Hello and welcome back to the Hyperthesis episode 68. Alright, it's good to be back in this cold winter. My name is Feely.
I'm Patrick.
And I'm Liam.
Well, today we're gonna take it to closer to home-ish, because we're gonna be talking about physics of the kitchen. So, but before we get into our main topic, anyone have intro topic? I know Liam, you do.
Yes, my main topic is also physics of the kitchen, it turns out. So we've got a double whammy today. And then Patrick's story later might be the triple whammy. So I found a paper, as I often do, titled Morphology of Bubble Dynamics in Sound and Heated Oil. So it's kind of similar to the champagne physics topic we talked about in a recent episode. I forget which one. In the sense that it's like this everyday phenomenon, more so than popping a champagne bottle is. So when you fry food in a pan with oil in order to cook it, if water gets into the oil, water and oil don't mix. So it causes this loud sizzling noise, and it causes oil to get sprayed out at you and burn your arms, and you get hit in the face and you keel over in pain screaming. Maybe it's not that dramatic. Maybe you just go, ow, crap. But anyway, oil spitting back at you and that sizzling noise. What's going on there? So this paper actually studies the physics of those phenomenon when you cook. So it's interesting because experienced cooks, they can hear these sounds and look at the bubbles in their pan, and it can tell them things about what they're cooking. They can say, oh, the oil's hot enough now for me to put my food on, or it's not quite there yet, or it's too hot, or there's too much water in this food, it's too moist, whatever. Chefs kind of have this intuition for it, and this paper wanted to better study the physics behind it. So this important interaction between heated oil and water has more implications than just cooking. It shows up in fire safety and indoor air pollution studies as well, but the paper focuses on just the cooking case.
Well, I think it's hilarious sometimes when I hear this, like, well, the chef knows better and stuff. Well, I mean, they do, but to me, cooking is like a basic skill, right? Like, I mean, if you ever cook, you kind of can tell that like the sizzling is different when the material is different, and when it's kind of found messed up. I think it's intuitive to human being too. I think we've been cooking for a long time in terms of humanity. And one of my policies that policy or rules, or I don't know, loose rules, that I don't trust scientists who can't cook. Because like it's literally following recipe. I have to understand two things: proportion and duration. And there's nothing more than that. I mean, when they're probably more, right? You want to be a
There's
chef.
definitely more.
Well, but if you want to cook for yourself, for example, right, it is not that hard. But you want to cook for the people, maybe following recipes, and opening restaurant. Being a chef is different. There's more than just cooking, right? And but like people who can't cook, like I don't think there can be proper scientists because how can you do you not understand durations and how ratios of ingredients work? Like, because like for example, like the easiest thing probably like boil an egg. Anyone should be boil an egg. If you're a scientist or try to be a scientist, because you understand how long 7 minutes are, and you have a clock or watch or some kind of clock, and you shouldn't mess that up. It's easier than a high school app. So, well, that's my opinion on scientific
I think
science and cooking.
I think there's a lot of scientists who probably can't do specific everyday life things, and they're scientists just fine. I don't think you
Yeah, I
need
don't
to know
trust
how to
them.
cook.
Oh, they're fine. I just don't trust them.
Oh, okay. Fair enough.
I would argue that anyone can be a good cook, but to be a great cook and, like, for example, know the temperature of your oil based on the sound that it makes when it sizzles. I think that takes a lot of skill, practice, and repetition to actually know. So, yeah, I think anyone can cook good, but to be able to cook great, I think you need a lot more practice. And much like this paper talks about, being able to distinguish kind of the different sounds is important, especially when you're working in a high intensity environment like in a restaurant. So it's lots of lots of tried and testing and all of that.
Yeah, and also they're studying it just to understand it as well. It does have applications in other places too. Um, but I think they just want to know like what's causing it, what's the mechanism going on. Turns out it's a bit more complicated than you think.
Well, it remind me of our episode with Troy, right? With welding, that a good welder can tell if the weld is going well, or is it, if the sound is correct when you weld. A similar thing, I think, is in almost every profession learn to recognize specific patterns on their on what they do, and what is a good one, what's a bad one. For scientists too, I guess. For physicists, we can recognize bad math or good math or such. So it's good. So those type of in reaction that happen, I think either is thermodynamic or chemical. So I let Liam get into it.
Yes. So the researchers in this paper performed two experiments, and you're gonna think the second one's funny. Um, the first one was they put a droplet of water into an oil bath, and this was like a preliminary experiment. They put some microphones around it, and they found that what happens is that these bubbles form in the oil, which expand, they become visible, and then they kind of explode and they emit distinct sounds as these different bubbles burst, and they spit out oil. And again, this is like common knowledge if you cook at all. Like even I know this. But the authors believed that it was worth studying further, and so they recorded this with their microphone, and then they performed their second experiment. And the second experiment was to come up with this kind of like minimal model of deep frying bulk food. So what they did, as any good physicist does, is they made approximations. So instead of taking a piece of pork and slapping it on a frying pan and seeing what happens, they took a two-dimensional piece of paper, moistened it, and placed it on the pan. So in other words, this two-dimensional moist piece of paper was it was meant to mimic what dipping food into a pan of oil, hot oil, does. And the fact that food has water content, the moist paper had water content. So I thought that was really, I don't know, I thought that it's like clever, but it's also kind of funny if you're a physicist because like you always hear the jokes about like you can approximate a cow to be spherical because it makes your math easier. Here they approximate it like a piece of chicken or something to be a 2D piece of paper. I don't know. I thought that's pretty funny. But it's like it's a good starting point, obviously. And what they found was when they dipped this paper into the oil, the hot oil, was that they found three distinct types of oil bubbles that form. So when the paper makes contact with the oil at first, initially you get bubbling at the interface between the two. You get the oil bubbling and bursting occurs as the oil surface hits the paper. This is followed by these craters which form in the oil. So there are these large dips at the surface, and they shoot back up and they create mist and splashes. So they splash oil around. And secondly, below this cavity, below this crater, you get these two cavity bubbles which form. One of them's way bigger than the other one and longer, and it actually moves downwards deeper into the oil. And then finally, the kind of third type was that what happens with this long downwards moving bubble is that you get this repeated expansion and shrinkage of it. So it creates these little jets that shoot back up. And what ends up happening is all three of these different ones. So your initial bubbles, your crater, and then this long oscillating bubble. They all make their own sounds. They all shoot out oil a certain way, and they all have a distinct signature. And they redid the first experiment with a single water droplet, and they ended up finding the same result again. So that way they could kind of match the sounds to each specific step in this mechanism. So kind of summarize the overall paper is that they found these three types of bubble events in the experiments: the initial explosion crater, this elongated cavity, and then the oscillating cavity. And I guess as well as the initial contact, that sizzling too. And they also found that it was nearly all temperature independent past a certain critical temperature. So as long as your oil was hot enough, it didn't matter too much if it was a little bit hotter or a significant amount hotter. The same kind of three bubble mechanisms formed, which caused this sizzling and oil to splatter out. But they did find out that the parameters which control the formation of these cavities and bubbles was the distance between the formed oil bubble and the water, as well as the bubble size. And I'm not quite sure exactly what controls that. Probably the moisture content in the water and how heavy maybe the food is pushing down on the oil. I'm not sure. But out of all the different bubble types, the oscillating cavity was the most violent and loud. So those are the ones that when you're cooking, I think they spray oil and it hits your arm or hand or something. And they're the loud, like, pops, I believe. Whereas the other ones are more so sizzly. They also found, using their microphone, that each bubble had their own kind of acoustic signal characteristic. So their own intensity, their own frequency, and their own duration. And they're potentially distinguishable, but they need to do more work on that front. So that might be why chefs are able to kind of hear specific things and know, like, okay, without knowing, they know that a certain bubble has formed, and therefore they've reached a certain point in the water-oil contact, maybe. Yeah, so there's some other applications I talk about, but maybe for the sake of time, I should just continue.
Did they talk about the Leidenfrost effect? Because I don't know, if the oil is very hot, it seems like that's gonna happen. I don't know if it's gonna change anything.
They might have mentioned it, but they didn't really get into it because they're not. I don't think they're so much concerned with what the water's doing. It feels like somehow when the water touches the oil, it causes all these things to happen with the oil. But I don't actually know what the water does. I think it might just evaporate. Maybe it just floats on top of the oil and evaporates because of the heat. But somehow this interaction between them causes bubbles in the oil.
Yeah. Just talk to elaborate on the Leidenfrost effect. It's just it's a reason why you can very briefly dip your fingers into liquid nitrogen and such, right? And because there's such a stark difference in temperature, and so like the liquid nitrogen evaporates so quickly around your fingers, so it's formed like this barrier of air, a pocket of air that protects your finger briefly from liquid nitrogen. So it's still not recommended to do.
And this is a cool experiment you can do at home if you have just a pan and a stove, is you can crank the heat up on the pan, and once it reaches a certain temperature, I think it's around 350 or 400 degrees Fahrenheit, which is around close to 200 degrees Celsius, then you'll see the Leidenfrost effect if you drop some water on there. So instead of just instantly evaporating, the water droplets themselves will just kind of float along and appear almost frictionless because there's this layer of steam that's beneath them that's essentially insulating them from directly evaporating.
It's like the water looks like it's on an air hockey table or something. It's bouncing around and floating about.
Exactly.
Yes, so that was some frying pan physics. This was published in 2002, so I don't know if there's more work going into it currently or not. I didn't look into it actually. And it wasn't like one of these, I don't know, it didn't seem like it was one of these huge implication papers. It was more just like a curiosity paper. There were some applications. They said that you could you could apply this to learn about deciphering sound signals with applications in acoustic sensing of aerosol generation, which they discuss a bit, but I didn't really read into, so I'm not sure what that means. But yeah, I thought it was kind of neat, as I do with most of the things I read.
All right. Thank you, Liam, for the intro topic. Well, and keep on with this thematic thing so of the kitchen. We will move forward to the main topic today, which is the physics of breakfast. Going to be spearheaded by Liam again.
Yes. So I was preparing for this yesterday. I found this paper titled "The Physics of Breakfast," which was published in Nature Reviews Physics in 2002 as well. So maybe 2002 was like the everyday physics year for scientists. I don't know. And this article really, it's a single page. It really nicely summarizes the kind of physics research that's gone into understanding some of the physics in your typical morning breakfast, and it cites all the relevant papers. There's 8 of them in it, so it's a really. It took me like 5 minutes or less to read. It was really good. So I wanted to kind of, for today's main topic, just basically paraphrase this article and get into some of the topics in a little bit more detail. So I've read the whole paper, and I've read some of bits of some of the site papers that it cites. But pretty much everything I'm going to say, maybe like 90% of it, is in this paper. So go read it. A lot of this is just me taking what they said and just rewording it and giving my own thoughts on it. And it was funny because I was in a colloquium yesterday on quantum information at McMaster, and it was beyond me. So I was just on my laptop in the audience getting ready for this talk, and everyone behind me was very interested in it. They're all leaning over me and like, "What are you doing?" And I'm like, "Pay attention to the colloquium, guys, not me. Come on." So other people are interested in this kind of stuff because it's just like it's a weird thing, right? Like, who would have thought of this? So this article it's kind of like a story. It starts off by talking about what happens. So when you wake up in the morning, depending what you're into, I'm not quoting it, but this is basically what it says. You might fancy yourself a cup of tea. So if you have some tea in the morning and you make your tea in a kettle, when you pour the boiling hot water out of the kettle, often what happens is that the water gets caught on the spout and it spills everywhere. And this is not due to you being clumsy. It turns out that just the design of kettle spouts is inherently bad for pouring water, which is a great shame when that's literally what they're designed to do. So the unfortunate shape of this spout and the fact that water surface tension causes spilling. But in 1986, physicist Jean-Marc van den Broek and Joseph B. Keller calculated the ideal shape of a teapot spout, which would not drip, and therefore, in principle, they solved the teapot spout problem. Because like if you pour tea every morning, that's really annoying to have to clean up hot water all the time that spills everywhere. And they actually won an Ig Nobel Prize for this, which is something we've talked about many times before. But to simplify their calculations in their work, they actually omitted the effects of gravity, which just possibly explains why, even to this day, many teapots and kettles which use their design still continue to drip, although they don't drip as much. So if there's anyone out there who knows about fluid mechanics, maybe redo their calculation, but with gravity this time, because turns out there's gravity on Earth. So for people listening who don't do physics, you might say, well, why the heck would they ignore gravity? That's so obvious. Often when you're doing math, it's hard. So to make it easier, you kind of throw away as much as you can and do it. So maybe they came back in the future and added gravity into their calculations, but it doesn't seem like they did, according to this article. So that's step 1 of your breakfast if you're a tea drinker. Step 2, maybe you want to dip a biscuit into your tea. Maybe you're British. Who knows? However, if you have a tea biscuit, eating it dry is not really a good idea, it turns out. Dipping it into the tea is, in fact, the best option. Because in 1999, Len Fisher found the optimal way to dunk a biscuit into tea. So because biscuits are porous, they display this capillary action. If you dip them into the tea and just hold them there, they will actually suck up the tea into them. You don't have to pump it yourself or anything. And that's something that shows up in biology, and you might have learned about it in high school. And after the biscuit absorbs enough tea, it actually softens and expands. And if you leave it in too long, it crumbles apart, which you don't want to do. You don't want to be fishing out crumbled biscuit from your tea. But once the biscuit absorbs the tea, the grains inside it actually dissolve into sugar. And this is why biscuits actually taste better when dipped. It turns out that they taste about 10 times better when they're dipped into tea because of this sugar generation. So I always wondered why dipping biscuits in things made them taste better. Not that I'm not a big tea drinker, but I've done it before. But also then there becomes the obvious question: how long do I dip it in so it tastes the best that it can without disintegrating in my hand? So Fisher calculated how long different biscuits should be dunked for before they absorb too much liquid and fall apart. And basically, you want it to taste good without disintegrating. And he found that, quote, the best way of dunking is at a shallow angle so that the bottom is wet but the top stays dry, end quote. So I imagine that the idea is that you get like kind of the surface of the bottom of the biscuit absorbed in tea, you bite it off, and then you go down to the next part, which is more dry, and repeat. These calculations were also in the absence of gravity for simplicity. I don't know what it is about these fluid mechanic guys ignoring gravity. Maybe, I don't know this, but maybe the Navier-Stokes equations are hard when you put gravity in. They probably are. But I think this result generalizes way better than the teapot thing, because the teapot mechanism really depends on gravity. I think ignoring gravity in this case is not a bad approximation.
Okay, when you say biscuit, is like not American biscuit, right? Like British biscuit, you know? Because
Good question. I didn't look into that. When I say biscuit, I imagine like a little bit of bread. I don't know.
Like a dessert, it's not like a Popeyes biscuit, but it's like salty. You eat with chicken.
Oh, I'm imagining the Popeyes biscuit, but not like the fast food version. I'm imagining like a nicer, smaller, denser one that was home cooked and not greasy and full of salt.
They definitely mean like a digestive cookie.
Yeah,
like that.
Yeah,
like just a small thin thing.
Yeah, you can get those at the store, even in Canada, little digestive biscuits. But yeah, I'm going to assume they meant a British biscuit, honestly.
I have a confession. I never dunk a biscuit into tea ever. Never done it. Never thought about it. And I don't think I had biscuit with tea ever.
I've drank tea like once in my life, and the one time I did, I dipped a biscuit into it, and it was one of those little digestive biscuits. I don't know why they're called digestive biscuits. Are they good for your digestion or something?
Apparently.
I always wondered that.
I had those before. I just, I'm not a huge fan. I don't know, the British people are going to kill me for this. I'm not a huge fan of destroying the texture that is already there. Maybe I don't know if it's really made to be dunked. Maybe that's what it was, but I just thought I like it crispy and dry.
According to this paper, they were made to be dunked because they taste way better when you dip them. If you like sugar, they taste better. But if you don't like sugar, maybe it's worse.
Yeah, I'm not a huge fan of sweets in general, so maybe that's why. Who knows? Maybe next time I'll try for what's it called experimental sake to see if it's actually better or if the soggy wet pastry would be worse.
Yes. So texture is also something which they don't talk about, but you got to follow the rules of this paper. You don't want to leave it in too long so that it gets soggy. You just want it to absorb just enough tea.
Well, and they eat it for breakfast. Breakfast.
I don't think it's their breakfast. I just think like sometimes at breakfast you'll have one. When I was in England for this conference a while ago, they have like little tea stations everywhere at the institution I was at, the Isaac Newton Institute, and they have like their designated tea breaks every day at specific times, and that's when you do a lot of like tea drinking with biscuits. So the British love their tea and biscuits for sure. It's not just a stereotype. I definitely experienced it when I was there.
It's like a fancy smoke break, but healthy.
Yeah, it's like it's like the slightly healthier version of a smoke break. Definitely. Okay, so maybe if you're like me and you don't like tea, well, okay, maybe not like me because I don't drink coffee either. But if you don't like tea and instead you want a coffee in the morning, this is another thing that people have done physics research on. So you make your coffee, you pour it into your mug, and you try and walk to your chair and sit down. But in doing so, you risk spilling your coffee everywhere. It turns out that, again, just like the teapot spout, this may not be entirely your fault. You're not as clumsy as you thought you were. Turns out physics wants you to spill your coffee. So in 2012, Hans Christian Mayer and Ruslan Krechetnikov, I believe. Sorry. They studied the physics of sloshing coffee. So this was a little more than 10 years ago, about 12 years ago, actually. So it's a bit more recent than the other things I've talked about. So they studied the physics of sloshing coffee, and they found that in your typical sized coffee mug, when you walk, you actually amplify the lowest frequency waves that are created within the mug, and you greatly amplify the noise in the mug. So you're kind of like, as you walk, you resonate the waves, and you walk in resonance with the waves in the coffee, and it causes it to oscillate more, and you have a more chance of spilling it over the edge.
I read about that a while back, I think, because they were trying to design a size of the cup so that, well, usually the liquid in the cup or the mug spill because of resonance, right? Because our pace create not vibration but like oscillation back and forth, back and forth. But if it's at the resonance, the amplitude at the edge of the mug would be really high and it would spill. But I don't remember exactly what they designed, but like there's specific shape or width of the mug that they should have. So it's really hard to spill when you walk because human pace have a specific frequency or like average frequency, and if you try to design the glass or the mug to not be that, or I think it's make it taller or something, it's really hard. It's much harder to spill, right? So I'm not sure we can touch on that, but yeah, I
Yes,
heard
I
the opposite.
am.
I heard it's like specific type of glassware mugs are really difficult to spill.
Yeah, so they don't talk about it too much, but I know um, they what they did in their experiment, which I can't quite remember how it works, but I think basically they just had like high quality cameras looking at their coffee mug, and they got a guy to hold a coffee mug and walk back and forth. So it's a pretty easy experiment to do. You just need some fancy cameras, and you need to be able to do math. Maybe it's more sophisticated than that. Probably is. I'm probably oversimplifying it, but um, yeah, typical coffee mug sizes, and I think this works with other liquids as well, which I scrolled through the paper for a while and I could not find anywhere talking about does this generalize for like water or other liquids. I'm assuming it does. Um, Coffee and water aren't that different from one another, although I'll come to that.
Viscosity is different.
Yeah, but it's not crazy different, I think. But I'll come to that soon. Actually, there's another topic involving coffee that comes up. Um, Different sized coffee mugs are more likely to spill than other ones because their kind of natural frequency is closer or further from the frequency of human walking. And it also varies on your height and how long your legs are and how far away your arm is from your body. But kind of like for your average person. And so there's a few obvious ways which they don't talk about, but like one way you can avoid spilling your coffee is you have a little lid on the top of it with a little hole that you drink out of. So, think of a Tim Hortons cup if you're from Canada and they have that little hole that you drink your coffee out of. I have a mug right in front of me that I'm drinking water out of, and it has this like more conical shape. I feel like that might help because it's narrower near the top and wider near the bottom. Maybe that helps you not spill it. I've never spilled out of this mug before, but I'm only drinking water out of it, not coffee, so who knows. But the other way, this paper proposes two different ways, which are a bit more complicated than the ones I've proposed. Two different mug types that could help avoid spilling. The first is that the mug was a more flexible container, which it could act as a sloshing absorber to suppress the wave oscillations That's a bit more complicated because if you're walking your mugs flopping around, that might be bad. You're probably more likely to spill it that way. But if you held it, if it was like you wrap your hand around it and hold it and it's a bit more flexible, it'll absorb the waves a bit more and they'll be less intense. The second way they proposed was that on the inside of the mug, you have a series of concentric rings on the inner walls of the cup. And what they do is they dampen the liquid sloshing around and they break the main resonant frequency into several smaller, less spilly frequencies. And these rings could actually have holes in them, which make better. They actually provide for better dampening, and they also would allow for the coffee to not get stuck between each of the concentric rings as much. But despite these two proposals they also comment on that even though these are two spill control options, their inconvenience probably far outweighs the convenience of just a regular coffee mug, which occasionally spills. And I think I agree with that. Imagine trying to wash that coffee mug with all the concentric rings with holes in them. That'd be a nightmare. I mean, if you have a dishwasher, that'd be fine, but I do not right now, so.
Well, I wonder if they study the effect of height of the mug too, right? I mean, I
Yeah.
guess it should be easier to spill when it's much shorter.
Yeah, they definitely consider that. But I think the height's not as big as a problem because it's like if you have a taller mug, then you can fill it up higher. But as long as your coffee is a certain distance from the top of the mug, within reason, it probably doesn't make too much of a difference, and it's only the width that controls your frequency. The height probably does
Well,
make a difference, but maybe less so. I don't know.
because like let's say like the beer stein for example, right? Like it's pretty hard to spill, and I think because the weight, they put the weight like a lot of weight on the bottom. So I think that's one of the solution too. I don't know if
Hmm.
you notice, right? When you
Yeah, that's a
carry
good
beer
point.
stein, like you see like well servers in Oktoberfest carry 12 of them at the same time without spilling and walk around, right? Like there must be a secret into that, right? Can we make a coffee mug the center of gravity different? Maybe it's heavier on the bottom, so it's less conducive to the resonance or the mechanical wave that come through to our body, and the distribution when when they rotate or the cup move is different, right? So
Yeah,
I wonder if that would actually dampen the spilling because I mean the Germans have been drinking beer for a long time, I think, and they there's a reason the bottom of the mug is heavier, right? So
that's
that
really
might be a reason.
interesting.
I'm surprised they didn't mention that or didn't look into that, or I don't know if they looked
Well,
into that. I didn't read the paper.
that's the beauty of research because pretty much every paper someone writes, any other physicist who reads it immediately says, "Why didn't they think of this thing?" And when you combine everyone's combined knowledge, you have like a really good width of topics and things. So, Feely, we should look into that. And if no one's looked into it, then there's a physics experiment we can do. Beautiful.
Amazing.
Yes, we science. Hell yeah. Um, and one other. So before I continue on to the next breakfast topic, the paper also says that you can help prevent spilling by walking slower and steadier. If you're walking too fast or accelerate too fast, it can give this frequency a big kick in amplitude, the waves of that frequency. And the other thing is that if you're walking pretty fast and it starts oscillating, you can like correct yourself and you can try and like walk against the natural frequency, but that feels a bit more tricky. But what's really interesting about this is that a high school student found I forget, I can't pronounce his name, Jiwon Han. I'm sure it's not pronounced like that at all. But this high school student did basically like a science fair project, and he found that if you walk backwards, walking backwards is the best way to prevent the coffee from spilling. And he won an Ig Nobel Prize in 2017 for his work. I don't know why that is, probably because you're going slower and you probably bob a lot less when you walk backwards. It's just mechanically different. But yeah,
You
you're
don't
less
walk the
likely.
same. You don't walk
Yeah,
the same when you walk backwards at all.
yeah,
I think it's
exactly.
completely different.
Yeah, exactly. So when you walk backwards, it's the best way to walk with coffee without spilling it. But then there's the problem of you can't see where you're going, so maybe that introduces you might bump into something and you're more likely to spill it that way. But it's cool that this high school student won an Ig Nobel Prize for that. I think that's awesome.
I think what the other way to make it less spilly is might make the cup really, really heavy. It's an
Yes.
expensive solution, right? Because now, Newton's law come into work because more mass, it doesn't move much, especially if it's closer to your body weight, right? Or not only our body weight, it'll be impossibly heavy for most people. And be closer to, let's say, like make it more homogeneous to our body and somehow dampen that effect just from the mass alone.
There could be more to it as well. Like I don't know if these beer steins, if the inside of them is circular or if it's like a octagon or a hexagon shape. I don't know, but I want to look into that now.
Usually
But then
circle,
yeah, I
easier to
thought
make.
so. Easier to drink out of too. But the next thing, so if you did happen to spill your coffee and it spilled down the side of your mug, and then you set your mug down on a table or on a book or a piece of paper, if you forgot about it and came back later that day, not only would you now have cold, sad coffee in a cup, but you'd have this coffee stain ring around the bottom of the mug on your paper or your table or whatever. And these coffee stain rings have a very distinctive shape and color to them. The ring that forms, the inside of it's way lighter in color. The outside gets much darker in the coffee color. And physicists in 1997, the physicist Robert Deganin and colleagues decided to look into this, and it led to a really large body of physics, actually. And they found that um, if you have like a little puddle or a drop of coffee on a desk, the surface tension allows it to keep its shape. But as the coffee evaporates, the liquid flows from kind of like the inside to the outside, and all the little coffee particles in the water, they get carried along with it. So what happens is that as the coffee evaporates, all the little coffee molecules and the things that give it its color, they push out to the edge and they get carried away from the middle. So what ends up happening is that when it completely evaporates, you get this ring of coffee on the outside, and the inside there's much less coffee. And I think we had a guest before, Pablo, a chemist, who talked about kind of the reverse of this, that he did some like work on what happens when you freeze food and how if you have these different particles, if you freeze water and you have particles of other stuff in the water will freeze from the outside to the in, so all those particles get pushed to the center. This is kind of like the opposite. The water evaporates and all the particles in it get pushed to the outside, so you get that distinctive ring shape. You can just Google it. There's a bunch of pictures when I did. And yeah, that's what they found. The coffee's been mostly pushed to the edge, and that's what gives this coffee mug its distinctive stain shape. And I was walking home. I read this yesterday, and I was walking home, walking to the bus home. And in Canada, it's snowy now, and when it snows, you put out a bunch of salt everywhere because the salt interacts with the ice. It reduces its freezing point, and that way, your roads are less likely to get frozen. Your sidewalks are less likely to get frozen. What I noticed is that there were all these coffee ring shapes on the ground, but instead of coffee, they were made with salt. So I think that's the same phenomenon as when you get like a little pool of salt water. So it warms up a bit. The salty snow and ice water mixture kind of melts into a puddle, and then it evaporates. All the salt in that puddle gets pushed to the outside, and you see that you get this distinct kind of like coffee ring shape, but with the salt as well. So I was walking home after I read that, and I was like, "Oh, that's got to be the same thing, right?"
A part of it is, I think, geometrical effect too, right? But seems like Hamilton still use salt, but here I think some
Oh,
part use salt, but around we use sand, because salt has become a problem. We use it a lot. It go to the sewage, and or some of it goes to the lake, and that's a
Hmm.
problem, right? Like a lot of salt go to the lake and it's destroy ecology, the balance of ecology. So I think it's more recommended to use sand, which somehow works because it's make the snow inhomogeneous, so it's harder to freeze. You know, you imagine you try to form a crystal structure and there are a little bunch of little pieces of sand everywhere preventing to form the structure. So it's a different effect. It's pretty interesting.
I think you can also imagine that if you have like a sheet of ice and there's sand on top of it, the sand kind of goes into the ice a little bit and then it becomes a rougher surface. So there's more friction. You're less likely to slip. All kinds of good things. Yes, that is a problem, salt. But I think it's the same thing. So I thought that was kind of cool. That immediately I noticed that. Another physicist, Peter J. Juncker and collaborators, they found that because these coffee particles, so coming back to this coffee ring, the coffee particles or molecules or combinations of molecules, they're more spherical than they are not spherical, which I don't know why, but that's just the case. So the stain is not uniform. So your coffee stain, it won't be this perfectly shaped ring. It'll have more coffee on one side than the other. And that has to do with surface forces. So if the coffee particles were instead ellipsoid shaped rather than spherical, the stain around the coffee mug would be completely uniform because these ellipsoid particles on the surface of water or a drop, they would more strongly attract each other in kind of a more symmetric way. And this attraction between particles of the surface of the liquid is called the Cheerio effect, which may appear in your morning bowl of cereal. So if you've ever had a bowl of cereal in milk, particularly Cheerios, which are shaped like little donuts, you might notice that you put them in, and the ones that float on the surface, they kind of once they get near each other, they stick to each other. They clump together, and even when you force them apart, they kind of re-clump. That's the Cheerio effect, and that's because it's the physics here is the same as the physics happening to the coffee particles in your spilled coffee. The Cheerios deform the surface of the liquid as they float on it, and this deformation causes the surface tension between the Cheerios to kind of pull at each other. So in your morning bowl of cereal, you might notice the Cheerio effect, which I definitely noticed as a kid. I definitely wondered. I wondered what was going on. I'd always pull them apart and they'd stick back together. And then I forgot about it until now. So I'm glad there was an answer to that. And finally, to wrap up your physics breakfast, you can consider some toast. There's this well-known saying that toast always falls buttered side up. It turns out that's not just a saying, it's actually somewhat true. In 1995, Robert Matthews found that the saying has some science to back it up. He found that toast, he did some experiments and he found when toast slides off of a kitchen table, that the side it lands on is primarily determined by the surface properties of the toast, so like how rough it is, and the height from which it falls. So I think the surface properties is that as it kind of spins and falls, it has some aerodynamic properties. And if it's very smooth, it's going to do one thing. If it's rough, it's going to spin another way. It's going to have more turbulence or less turbulence. And the other parameter is how high it is from where it falls. So is the table really high? Is it really low? Because the higher the table is, the more time it has to spin. The lower it is, the less time. And doing this experiment, they found that for your average, well, I guess the butter on the one side of toast also matters because that makes one side more smooth than rough. And for your average piece of toast, for your average table height, whatever that is, I didn't look into it, but they found that it's significantly more likely for your toast to land on its buttered side than the unbuttered one. So as it falls off, it happens to rotate due to the kind of interaction with the air and how far it is. It gets this net torque that spins it. It's more likely to land on its butter side up.
Well, the initial condition is fixed. Nobody put their butter side downwards when they butter it, right? Like, and
Yes.
so every time it falls off, it's gonna start with the butter side up, right? So if it spin and for a certain velocity or angular velocity, I'm not surprised that it's gonna land the butter side down. right? But it's unless it just land like if there's no torsion or like there's no spin at all.
Hmm.
So
But I think in his experiment, he imagined that you're like that it slides off the table, which I don't know how likely that is, but I can imagine if you're holding a plate and walking, the toast could slide off pretty easily. But if you're sitting at a table eating it, it's a bit less likely. But I think the results kind of generalize to if a little bit above the table. It's your initial condition that basically depends on how it lands. But he found that it often lands butter side down, so it always lands on the butter side, um, more often
somehow
than not.
somehow it reminds me of like study of how cats fall. And I
Hmm.
think there was that like is above 20 floors the survival rate goes up or something. It's a little bit a despicable experiment. Actually, not a little bit. It's a despicable experiment. I think what they found is like the survival rate at like 7, 8 floors is 0 or something, but with above like 12 floor or something, it's like oh they survive. I don't know how that works, or maybe that's not a real science, which is a myth. Maybe I need to confirm that, but people threw cats off building is not exactly ethical
I hope they
scientific
did. I hope
experiment.
they didn't actually do that. That's crazy. But coming to back to the toast and not throwing cats off buildings, Matthews also gave a potential way to save your toast from landing on its buttered side if it falls. So he said if your toast slides off the table, instead of just watching it sadly plop on the ground and get hair and whatever on the butter side, just smack the toast as hard as you can. So if you smack the toast when it falls off the table, you're basically adding a large horizontal velocity to it, and you're reducing its spin. So even though it's going to fall the same distance in the same time, it's not going to be spinning. There's a chance it's not going to be spinning as much. There's also a chance I think that's going to be spinning more. But if it's already likely to land on the butter side, it's worth taking the shot and hitting it. So smack your toast, and hopefully that you give it the right amount of spin that it doesn't land on its butter side when it hits the ground. Because I feel like if the toast hits the ground butter side down, like all the little dirt and thing, it's going to stick to the butter. But if it lands on the non-buttered side, it's not going to stick as much. So you've got a better shot.
Imagine you see some kid is like drop that toy, just start smacking it. Bam! I was like, why you do that, son? It's science, dad.
I don't eat toast enough to even like test that theory. So I think by the time I remember to smack it, it'd already be on the ground. I don't think my reflexes are that fast.
Skill issue again. A lot of things
Yeah,
skill issue, Liam. You
it is
drop
a
it in the
skill
first
issue.
place. Yeah, exactly.
Yeah. But anyway, that's kind of what this physics of breakfast paper talks about. All these different things, and they didn't talk about frying oil, so I added that topic in on my own because I felt like you cook an egg in the morning or whatever. That's kind of breakfast physics. I always really like these everyday physics topics that we've talked about before, and they have all kinds of surprising applications outside of just the simple situations. So, for example, the coffee particle and Cheerio effect physics has applications in printer inkjets, apparently. The teapot spout has applications in production lines and so on. So you do some simple physics and you realize down the road that there's something you can use it for.
One thing I find different about this, I want to point out that those what you call breakfasts is like weren't my breakfast growing up at all. Like those were not like it's rarely breakfast. Like cereal. What the heck was that? And put in milk and toast, bread. I think it's a lot of cultural difference there. Growing up, it's like no,
Mm-hmm.
none of those things were like maybe like from time to time when my parents were bored or something or like didn't want to cook proper breakfast. That was the breakfast.
Yeah, well, even for me, growing up in Canada, I think out of all of that stuff I talked about, Cheerios was the only thing I would have for breakfast out of all of those. Like, I never had toast for breakfast. I didn't drink coffee or whatever. I just ate Cheerios for breakfast a lot of the time.
Well, I had like, rice stir fry, special type of noodles, steamed buns. There are like multitude of breakfast food that not like, a lot of food here, especially for breakfast, is I think predicated on the convenience of making, right?
Mhm.
Because to eat out for breakfast is expensive, while growing up back home is much cheaper to even eat breakfast. Say in high school, I ate breakfast at school. I just go to school at like 7 a.m.
Mhm.
They have the canteen open since like 6:30, and you have whatever you want for breakfast. And it's like
Well,
at the time it was like less than $1 Canadian each.
that
So it's
that is the
yeah.
dream.
Yeah, you can eat like good food that's is breakfast food, like porridge and stuff, and even non-breakfast food is fried. Usually fried foods is not recommended because it's you get sloppy during the day. But it is such a different thing. Like those people consider breakfast here to me is a little non-breakfast to me. It's a little too I mean I'm used to it now, but it's a little strangely simple.
My current yes. Okay, I was just gonna say my current breakfast is just a smoothie every day. I love me that smoothie. It's like my version of coffee. But anyway,
Oh, I have a banana for breakfast and maybe like a banana smoothie with oats for some reason. But well, I mean, let's not talk too much about our digestive scheme. So
oh, well, actually, we will be.
well, that's why we don't talk too much now because Patrick gonna be telling a story about our digestive system, and before that, Patrick gonna tell you how to reach us. And thank you, Liam, for the main topic. Is a very physicist way of looking at things. Sometimes you see.
Ignoring gravity when pouring tea. Yeah, that's pretty it's pretty theoretical.
Yes, so remember when you're walking with coffee or doing anything with coffee or breakfast, just ignore gravity, float, be like the astronauts on the ISS trying to get their breakfast through squeeze tubes. But aside from that, we'll get into what happens with the food and coffee when you drink it and eat it. But before then, I want to tell you how you can contact us. So we have many different ways in which you can reach out to us. We have an email. We are hyperthesispodcast@gmail.com. And we also have an Instagram account. We are found at the Hyperthesis, where you can check us out for updates. You can follow us so you make sure that you know when an episode has been posted. You can also reach out to us over DM, where if you are an expert in your field, whether it's food sciences or food physics, which we know a couple people who do that, or at least one person, we would love to have you on the show as a guest where we can pick your brain about what you do for research or just what your area of expertise is in. So again, that's at the Hyperthesis on Instagram, and you can reach out to us anytime. If you are listening to us, congratulations, you found us. We are on many different podcasting services. We're on Apple Podcast, Google Podcast, which is going away quite soon, along with Audible, and we are based out of Spotify. So if you have the option, feel free to give us a rating or a review. If you leave a review, that's even better. And feel free to subscribe to us, share us. We are trying to spread the word about the Hyperthesis, and we want to reach a wider audience, which is why we also have a YouTube channel. So you can check us out on YouTube. Just search up Hyperthesis Podcast, and you will find a pretty much up-to-date list of episodes for our channel. We might be a couple episodes behind, but that's because our lovely videos take a while to process. We also post some additional content to the YouTube. Were some, I guess, rumblings last week that there was extra content, but it doesn't seem that that extra content is satisfactory. So I have some actual shorts to post up on there, which should be cool to watch. So keep an eye on that. Subscribe, like,
Ooh.
comment, do whatever you need to do, but give us a follow and a listen and share us with your friends, family, or even strangers and enemies. And thanks for listening to the Hyperthesis. So moving on to today's story, keeping with the theme of food and eating and all of that, we are going to focus on an incredible journey that is undertaken billions of times a day. And this journey is violent and nothing will make it out alive for the most part. This is a story of how fuel is made and of how energy is not necessarily created, but changes forms, and is a story of how we eat food and how that food undergoes digestion. So we'll be starting at the very start and then ending exactly where you expect food to end up. But we do need all this food for our bodies to grow, to move, to heal, and to remain alive. Now, different people can go different lengths of time without food. Typically, for a person, it's about 2 days without water before you might die. But people have gone without food for extended periods of time, whether for hunger strikes or for medical reasons. But not eating will catch up to people eventually. Now, the digestive system is designed to try and extract nutrients from food and as much as it can, and it's breaking down complex molecules into simple glucose and amino acids and fatty acids. And something like a sandwich is processed in the digestive stream to be eventually absorbed into the bloodstream and remove any additional waste. So to start with our digestive journey, we start with the thing that I'm using now, which is my mouth, or your mouth, or anyone's mouth. Now, the mouth contains both physical and chemical methods of breaking down food. The physical, of course, are quite obvious. Your teeth. Humans are very lucky in that we are omnivores. So we have teeth that are designed to tear away and kind of cut more difficult food like meat, while we also have back molars, which are able to grind food, especially leafy foods that break down those complex, very rigid structures. Now, of course, our teeth are able to grind and to mash and to tear food into smaller pieces. And we also have a couple glands, such as the parotid glands, the submandibular glands, and the sublingual glands. Now, all these glands are able to produce saliva, which helps wet the food and makes it easier to swallow. If you've ever had to swallow dry food, such as a dry digestive cookie or dry or biscuit, in case you don't dip it into your tea, you'll know that there's some difficulty there. There's also a swallow test that you have to do where you can't consume water for many hours beforehand, and you just swallow this dry kind of pop rock material, and it's disgusting. But luckily, you have salivary glands that can make things a little bit wetter. The saliva is not only great for wetting your food and making sure it can be swallowed easier, but they also have enzymes. And these are special digestive enzymes that are able to help digest especially starches in your food. So for an example, one of the enzymes is called amylase, which breaks down starches or complex carbohydrates. So the next time you're digging into a thing of potato chips, think your amylase that's produced in a part of your saliva, which will help break down those starches. It also has other enzymes which can break down fats, and it really starts to get digested as soon as it enters your mouth. Now, just a quick side note, saliva also helps you taste, because once food that enters your mouth gets wet, it's able to interact with your taste buds, and so will interact differently depending on what is contained in the food, but it's thanks to your saliva that you're able to taste better. Now, moving on from your mouth, it's swallowed down the esophagus and makes its way through essentially a long series of muscles, kind of like a snake almost, where their muscles are able to force the food down towards your stomach. And a fun fact, people are able to drink upside down, but that's not true for all mammals. But you are able to swallow, the food goes down into your stomach, where it's digested quite violently by some stomach acid in there. So your stomach, of course, will produce acid, which will begin to break it up even further, dissolving more complex molecules into simpler molecules. And it is able to really start breaking things down quite efficiently, Now, the stomach uh, is able to hold quite a bit of food, and when you feel full, that's most likely because your stomach is at capacity.
Well, one proof that esophagus doesn't need gravity to push down is that humans live in space, right? Like international space station. Well, it doesn't. Well, it's weightlessness, but it still experiences a lot of gravity from Earth. But it's counteracted by the um, orbit of the space station. But they can eat and drink just fine, and I think you can do CT scan. You can see basically how the esophagus enveloped the food and push it down. Right? It's actually it's a fascinating thing, right? Like, and maybe some animals can do that and they can't live in space. So,
Yeah, so I guess we'll have to find out in the future what animals we can take with us to Mars. Regardless of that, also in the stomach, aside from the gastric juices that help break everything down, it also does a lot of churning as well. And so that mechanically breaks down the food along with the chemical addition of the acid. Now, here, there's a nice sphincter at the end of your stomach where food can enter. And you'll hear the word sphincter a lot, which there are sphincters kind of all along your throat, which help force the food down. There's a sphincter at the end of your stomach as it goes into the small intestine. Now, this first part of the small intestine that the food enters is called the duodenum. And here, the food is mixed with more digestive enzymes from both the pancreas and from the liver. There's some question and still research going on about the gallbladder, but essentially, there's a lot of work going on here to further break down the food and make sure it's ready for the lower parts of the small intestine. Now, the small intestine is also able to squeeze this food along as it's broken down, much like your throat, so that it's not just sitting in one place, which would be not non-functional pretty much.
man, I kind of want humans to have like a gizzard. Like we eat small rocks, so we can break down those seeds. It'd be so much fun. Or is it kids try to eat rocks anyway, right? Maybe there's some evolutionary thing there. And the second thing is like what I remember from biology class from like small intestine is that I think it started duodenum and jejunum, but then ileum, right? And then you go to the big intestines. But that's probably the extent of my biology.
Well, you nailed the names because once the food is passed through the first part, the duodenum of the small intestine, it then moves to the jejunum and the ileum. Got it right? Where in the ileum, that's where nutrients are actually absorbed. So this is lined with millions of finger-like projections called villi, and they have blood vessels in them or capillaries in them where nutrients are able to cross that barrier and enter the bloodstream.
It's active
And
transport, right? Like when they absorb, it's not us. Well, I think because well, there's a reason why they also don't like, oh, don't drink pure water, right? Just like deionized or distilled water, because it's actually instead of absorbing the minerals from the water, it's actually the minerals from your body. It's going to the water. I don't know if that's a myth, but I feel like that's true.
you definitely shouldn't drink deionized water, but that's mainly because it will overfill cells. Because if there's no ions within the water, then it will try and balance it out by flooding your cells and causing them to burst. So, not the
Okay,
best idea.
So it's not that the minerals go from your body into the water. It's the it's osmotic pressure. It's osmosis into your cell and burst it. Okay.
Exactly. Yes. So don't drink water that's being distilled. So don't drink pure water. Make sure there's some minerals in there, which will also help with digestion. Now, in your small intestine, these nutrients and minerals are absorbed into the bloodstream, and the pancreas is able to help out with that. So, as well as secreting digestive juices, it's also able to release a hormone called insulin, and this is able to help regulate the amount of sugar in the body by essentially binding to cells and letting the sugar enter. So when you have diabetes, where you need insulin, your pancreas isn't able to produce it as much or at all, and so that those sugars can't really enter your cells. Now, the liver has many roles. We won't get into them. Honestly, we could do a whole episode on the liver, but it's useful for breaking down fats and also using bile that's stored in the gallbladder. It's able to process proteins and carbohydrates. If you've ever had a night out of drinking, your liver is also able to do that. And then it's also able to filter other things, especially red blood cells. That's where red blood cells go to die. And then they enter your large intestine, which once all the nutrients are removed in the small intestine, water is moved into the large intestine, or the bowel, as it's also known as. And here, water is removed, and the waste is stored in the rectum. From there, it just kind of sits there until it's ready to be passed out of the body through the anus. So what you're seeing in your stool is waterless because it's been absorbed. So dehydrated, mostly substance that gets its color mainly from red blood cells that have been pushed out of the body because their time is done.
Yeah, I remember that, like, in the large intestine is where the water is absorbed, right? Like, and to make it, like dry. And another fun fact, wasn't it the intestine's human body? It's like if you, take it out, line it up, it's like 35 or 34 meters or something long, right? It's really long, but it's like it's all what's called bundled up inside the body, but it's a very long organ.
Yeah, I think it's on average about like 25 to 30 feet, which is about 8 to 10 meters, we'll say. So there's quite a lot there, and there are some gross world records you can read about concerning people using that to their advantage. But regardless, it's very interesting the fact that we're able to eat so many different types of foods. And one thing I forgot to mention is in the intestines, we have a whole bunch of different bacteria, which is able to help break down and process these foods, and is incredibly useful in a very mutualistic relationship. So there's a lot going on in your body.
Yeah, I think it's called the gut flora, right? And different people from different region have different ones because what the food they eat, the fruits and vegetables and things that are around. That's why I think when you go to a new country that's far away, eat the food for the first time, you might get your stomach get upset, your bowels get upset because you're not used to that type of bacteria and such. But after a few weeks, you'll be fine, right? And I'm talking mostly for like fresh fruits and vegetables that you're not used to. Usually it's cooked. When it's cooked, those bacteria died off, but there's still some anyways. Yeah, anyways, thank you, Patrick, for the story. Episode 68. We ate a lot of food and cooking kitchen today. I hope you have something to, you learned something new today. So that's good. All right. Thank you, everybody. I'll see you guys next week and take care.
Bye, everyone.
Peace.